Hello, welcome everybody. Thank you so much for coming in early and taking the seats. We have a full house. I hope you guys have been enjoying yourself. Apologies for a few minutes delay. Um, Welcome to the Out-of-Box Network Developers Meetup, SDN and Switching Meetup, SFA OpenStack Meetup. Welcome to Intel. So I'm Sujata Tabrewala. I'm the networking evangelist here. My role is to build community around networking. So I take care of what we call it Intel Developer Zone. So the Developer Zone has various other technologies like RealSense, Game Dev, Model Code. I take care of networking. So here are some of the things which I do. So we have the Intel Developer Zone website, which features content from Intel and from outside of Intel who are working in SDN and NFV area. We conduct live developer trainings. That's basically the main focus of community development, because community development cannot be done offline. So we want to meet people. We want people to meet each other. We have a platform called DevMesh. You can say that is Facebook for developers. So developers can feature the projects, and they can ask for collaborations, and people can follow projects. We have an innovator program for people outside of Intel who are working on SDN and NFV technologies. We feature them on our developer zone, and they get, if they have their speaking opportunities at conferences and all that. So basically, we put them forth for our developer training. So these are some of the upcoming events from the zone: OPNFV Summit, Red Hat Summit. Some of you might have already heard of the DPDK Summits, which are held in US, and there is Intel Developer Forum. We're going to do a DPDK deep dive session in July here. That would be a limited session, that would not be like this. So once we announce it, we would announce it on the meetup as well. So the goal of the community building is to foster learning and innovation. And like I said, it's really a platform for people to meet each other, interact with each other. The presentation today, which we have, is in collaboration with Intel and Google, is a great example. The speakers did a very good job of, talking to each other, come up with a, collated slide, collated story. It's going to be beyond today's presentation. They're going to take it forward. So that's our goal, to build the community and to have something come out of it, something concrete come out of it. Of course, to drive open source adoption and inspire developers to solve problems in the SDN and NFV industry. So with that, let me introduce the team, the Google and Intel team. I would really appreciate if the team can come forward and introduce themselves.
No, we got it. Anybody know how to drive a Microsoft Surface?
You did that.
How did he do it? Yeah, the long chalk. Duplicates. Yes.
Oh, that's why it's already wrong.
Well, let's get going and let's at least introduce ourselves. My apologies for a few technical issues here. So, my name is Edwin Verkijk. I'm a principal engineer with the Network Platforms Group. We changed our name recently. And we're the division at Intel that basically builds communications equipment. So, for those folks that don't know, we build silicon that basically accelerates the internet from many angles. So, we build a compression complex, crypto complex. We are responsible for some new instructions. And the folks that are with me here, Priya and Rashmin, will introduce themselves in a minute. But yes, Intel has a network division, so that's why we're here today. And then two folks from Google are joining us today as well. They're going to introduce themselves in a minute. And we're going to cover a broad spectrum of the technologies. I encourage you to ask questions, but if it gets a little bit long, we'll try and take them offline and talk to you guys after the meetup. So what we'd like to do is paint a picture of today's networking environment and what we're doing to change that. So we're going to talk about network functions virtualization, SDI, and some of the key components that we've developed to basically support that build out. And yeah, a little bit about ourselves, I suppose. So I'm an engineer. I spend most of my time in our labs. Occasionally they let us out to do these talks. So if it's if we have these kind of technical issues, and, if we're not quite meeting your needs, let us know. We're all technologists. So, and with that, you want to introduce yourself, Rashmi?
Hello. Hi. Hi. My name is Rashmin Patel, and I'm a software engineer focusing on DPDK virtualization for past 4 years, and we have started virtualizing telco workloads for like 5.5 years now, and we know the whole journey they have gone through and what we have in rental architecture to support them. So I've been focusing on this networking issues and packet processing APIs around the telco for a long time. And with that,
Hi everyone. Can you hear me?
Yes.
Yes. Okay, I'm Priya. I'm from Intel. I'm part of the same group as Edwin and Rashmin. And I have been working on Intel's Resource Director technology, which was a hero feature on board with EP launch. Some of you might know. But but I have been mainly focusing on getting this feature into software stack and different software initiatives. So yeah, from that I will just let Jen introduce himself.
Hi, I'm Jayan. I'm an engineering director at Google. I work in our network systems organization, and network systems and cloud networking. And specifically, I'm responsible for teams that build our RPC frameworks, RPC systems. We've been building it for a long time. 2 years ago, we decided to open source it, and we are developing it in open source with the intention of harboring a great ecosystem, open source ecosystem. Looking forward to all of you using, adopting, contributing, and growing this ecosystem. Thanks.
Hi, I'm Abhishek Kumar. I'm a technical lead on the gRPC project, and I've been working on RPC systems at Google for the past several years. As we'll see later in the presentations, Google has always internally used RPCs as the networking abstraction for communication, inter-process communication across our distributed stack. So I've been working on that effort for several years now. I'm delighted to bring gRPC out in the open and have it be developed with the community.
So, a little bit about the agenda. So, how RDT, the Resource Director Technology, and gRPC fits into the software-defined infrastructure, software-defined networking, network function virtualization, and OpenStack. I know these are a lot of keywords and acronyms, and like Edwin said, if any of you do not know about these acronyms, please don't be afraid to ask questions. So I would give the overview of how these fit in, and then Edwin and his team would talk about the key platform requirements for the software-defined infrastructure and the ingredients for the SDI, DPDK, and Intel Resource Director Technology. Then Abhishek and Jeff would talk about the RPC service framework, and then would conclude the talk with how these two fit together to solve the problems in the NFV and service delivery. So, just to give our 10,000 meters overview of how SDI, NFV, SDN, and OpenStack work with each other. So how many people in this room know all of these acronyms? Don't know these acronyms. Don't know? Okay. So SDN, software defined networking. So let me just.
What is SDI?
Sorry?
SDI.
So software defined infrastructure. So basically, this is one solution, software-defined infrastructure of how it could be implemented. So it has the components.
Are you going to share a slide?
Yes.
How?
If they will be posted on the meetup. Yeah. So you have the three ingredients of the software-defined infrastructure: compute, storage, and networking. And you have the OpenStack, which helps orchestrate. Now, RDT, the Resource Director Technology, is close to the hardware, which ensures that when we are virtualizing the functions that we are virtualizing, they still get the hardware resources which they demand, right? So, if people who have worked in this area, they know that virtual machines are not known to have the similar performance as when you implement the same function on bare metal, right? So resource director technology is something which is trying to fill that gap, and this is close to hardware. And gRPC is something which is close to the orchestration. So, so this talk is how gRPC and RDT come together. And the speakers would be talking in detail about this, so I would give the floor to this.
So it's maybe I'll collaborate a little bit. I think I want to make sure the audience kind of gets this, because if we don't get this bit, then kind of all the other pieces go lost. So fundamentally, what we've been trying to do is, virtualize network equipment, and ultimately, how gRPC fits into this is by the ability to effectively let these devices communicate to each other. So that's kind of where that fits in. But at the lower level, the more, if you start consolidating communications devices, it gets kind of complex, because these are typically designed for peak performance. So take a router, or take a wireless gateway, or take the antennas that you see in the field, right? You see all those big antennas with where we do the analog to digital conversions, and then it gets shipped down, and then your internet packet ultimately goes into the internet. But there's an enormous amount of communications equipment that fits in the middle, and all that stuff is designed for peak performance. The problem with that is it's really expensive. And what if you don't need peak performance? What if you're during a time of the day where it's at night, or some portion in the time where everybody's having coffee? You don't need that amount of throughput that device requires. So fundamentally what we're trying to do is take all those communication devices and virtualize them. And that's, to a certain extent, what we're trying to tell you here. So you see all these layered applications, see all these kind of management pieces, but fundamentally what we're trying to tell you here is, hey, you know what? We have a more efficient way of virtualizing communications appliances. It makes sense, because as the number of users grows, and as the amount of traffic grows, the amount of investment that telecommunication suppliers needs to make, people like AT&T, Verizon, is huge. And actually their investment in that equipment is actually outpacing the revenues they can gain from the services. So that's a problem for them. And that's fundamentally what we're trying to fix. So keep in mind that from now on, what we're trying to do is move these communications devices, right, these routers, gateways, wireless equipment, we're trying to move that into the data center and backhaul the access into the data center. But then you've got certain problems, because now you're consolidating. And if you're consolidating, you're gonna go and compete for shared resources. So those are some of the things we're going to be talking about in the next hour and a half or so. We're going to be talking about accelerating the packet delivery through DPDK. We're going to be talking about the ability to partition the platform so you can maintain those performance requirements. Right? Like I said, if you're going to consolidate, you need to be able to isolate portions of the platform. And we're going to be talking about that. And then lastly, at a much higher layer, you need to be able to efficiently communicate between these various virtual machines and services. And that's where our Google colleagues come in. So that's fundamentally what we're trying to do.
So,
Sorry, go ahead.
so when you say consolidating the data center, then you're moving the access points away from the end user?
Yeah, actually, that's fundamentally, we have an initiative called Cloud RAN, so Cloud Radio Area Network, where we're essentially doing the first portion of the processing at the cell tower, everything else backhauled into the data center. And that's a well-known concept. And it makes sense, because that cell tower, the more equipment you put at the bottom of that, the more difficult it becomes to manage and the more expensive it gets. So it kind of makes sense to move that into the data center, where you have, hopefully, access compute capabilities, and you do it there, rather at these cell stations where you don't necessarily have the power or the infrastructure to support those number of calls that you want to.
So isn't that going to conflict with VCPE? Virtual customer presence equipment?
No, I don't think so. I think that's VCPE is essentially an appliance that typically lives in small to medium-sized businesses, or even in the home, where you're consolidating certain services, email, communications appliances, firewall, that's correct. Right?
Yeah.
So what we're not necessarily saying, ship that back, right? But the access to that you might want to ship that back, which is a different sort of device. The VCB element that you're talking about, we're actually trying to virtualize those elements and make those live on the same sort of standard server hardware rather than on specific devices. Yeah.
So then,
But does that make sense?
yeah, okay. But now, the follow-up is when you say consolidate the data center, which data center? Because you have this big data center, you have AT&T, the Verizon,
Yep.
whatever.
Yep.
But then they also aggregate out to smaller players. Do they
Yep.
sort of wholesale their bandwidth and stuff?
Yeah.
So,
Phenomenal question. I don't think I have the answer. I do know that big telcos, they look into develop, shouldn't use telcos, they should use the word probably communication service provider. They prefer to be referred to as that. So they are typically building several massive consolidated sites throughout the nation, right? And then yes, there are smaller sites where they don't have the same kind of coverage to support that. So that's why you see this still somewhat of a distributed approach, but that's the reason why. But let's take that one offline, because I can't answer for
okay.
service providers. There was one quick question there.
I think, in this architecture, how are you taking care of latency? Because as you go to 5G and stuff like that, there's more requirement for low latency. How does
Phenomenal
it?
question. We'll talk about Intel Resource Directed Technology, where we're actually partitioning the standard server hardware, and we'll talk about it. So I hope that kind of positions the talk, so you get a feel for where we're trending and why these three individual pieces fits into that. So, and with that,
Yeah.
are you okay?
Yeah.
Rashmi?
So thanks, Edwin, for giving that background. It was really needed to set everyone on the same page. So in last for 4 or 5 years, we have seen a trend where all this communication service providers, they have been consolidating their different kinds of workloads in the same platform just to consolidate that site and get the most out of resource utilization. But then later on in last 2-3 years, they have been trying to consolidate all those workloads on the general purpose IA processor, where they have been running compute sensitive or network sensitive workloads, or in some cases storage as well. And that's where we have been trying to support those guys with our key platform ingredients. For example, data frame development kit, which is an optimized IO API, IO access API, which gives you a better latency when you access the packets from the network. And the next one is we have virtualization technology. So suddenly these guys took their network virtualization, their network workload, and put it inside a virtual machine. They saw so many bottlenecks and overhead because virtualization wasn't ready maybe that time for comms, and eventually we provided some of the virtualization hooks in the hardware, and because of those we could reach up to the native performance.
Yeah, perhaps it's again the clear distinction between compute and networking, right? So compute virtualization works phenomenally well, right? Or at least for the majority of the workloads. We have huge amounts of hooks under the hood that allow you to near native performance. And the kind of stuff that Rashmi is pointing out is things like posted interrupts, page modification, logging, other enhancements specifically for communications that we've actually accelerated as part of the virtualization instruction set. Sorry.
So when you were saying about what you were just saying with the hardware information, you were talking about also interconnected switching, right? So we have a network where you are running a signal from the wire, where you are virtualizing it in the center. So when you were talking about interconnect, where is the non-volatile NVM technology fits into this picture at Google? Or, well, I know that Intel is banning it, but like NVM over fabrics with NVM over locally moved NVM when you are storing data and manipulating data over the virtual machine.
Want me to get that show? That's a pretty difficult question. So fundamentally, what you're asking is, for the rest of the audience is, okay, how do we take advantage of 3D crosspoint, right? So we have this new, for those folks that don't know, we have new non-volatile memory infrastructure that actually sits on the memory interface, which is great because it means that you can do away with a lot of the storage requirements. And I'm not sure whether I should have said that, but the point is that you have this technology that basically non-volatile memory that sits on the memory interface. Now, how is that exposed? There's a couple of ways. It's either through app direct, or it's through a block mode operation. Those are the two. Block mode. So you get a new device. You get a block device, and the block device you talk through from your application, and it basically means.
Blocks around CPU or blocks around the...
No, block is actually in memory. So you have a block, just like you have a driver, you have a character device or a block device. You get a block device. That's what you talk to. Second way is app direct. Your application can actually tell the OS that I want to write to this kind of memory because it's viewed as a type of memory. Now the next question is, how do you expose this to everybody else? I don't have the answer, and I don't quite know from a big perspective where that fits.
Well, I know there is the NDM Express, which tracks
Okay.
the effort.
Okay.
I know that the Amber and the whole Intel tracks the initiative. I know there were some talks in the Open Server Summit about that. I know that Flash Memory Summit, which is in August and September,
Right. You're saying there is a high level piece of software that already takes advantage of it. Like I said, we're communication, so we don't necessarily know where that piece is.
So it's agnostic to you, right?
It's agnostic to us. If the application wants to write to that new type of memory, by all means, we don't really care. But there is one element you do need to know. The latency is slightly higher. It's way faster than this, but it is still higher than standard memory. So if you're doing packet processing, probably not where you want to store your packet data.
No, it's actually faster than the standard memory.
We could take that up.
But aren't you trying to put an infrastructure in place to be able to identify those things and properly assign them to whatever
Absolutely.
application? I think that's what I heard.
Absolutely. That exists. I was talking about the mechanics by which you can get to that type of. She's absolutely right. There must be higher layer software that exposes it to the applications around, so you know what you're going about.
Yep.
But this is not about. This talk is not about it. So this is about on the other end of the spectrum.
Yeah, and I believe that memory wouldn't help everyone. It will be like use case to use case. You have to change it based on your use case. You can use it in the block mode or a memory mode.
Now, in-memory databases, outstanding, right? So if you have something that you want relatively quick access to, and you can't afford 64 gigs of memory, well, then you stick it there because it's cheap and massive. Anyway, I should qualify it. It might not be cheap because I don't know. So anyway, sorry, we're derailing. Let's get back on you.
Yeah. So in any case, that virtualization shift wasn't that easy. So we have a couple of technologies lined up here, and one of the key technologies is resource director technology that we launched with broad LEP, and it provides provides your services of protection against the shared resource contention, and that's what Priya is going to talk about in the next slide. So I just want to keep it forward. And keep in mind, the communication between that end users and back-end public or private cloud is not really an over-the-night change. It's all about highly exploiting users' data, and people have been using their mobile apps and services all around the store, and that's what increases and gives that to get a bit big. And that's why we have been doing some of the optimization. Let's do a deep dive. The last slide was a 10 kb high. Yeah, sure. So this is a little bit closer view to the platform. Better 5K feet, I believe. Yeah. So whatever reason, from flexibility or scalability, service agility, or resource utilization, we have seen this different kinds of services deployment scenarios on Intel platform across different kinds of infrastructures, like different private, public clouds and things. So the key types of these services I have kind of tried to summarize, but it's not really easy to summarize those in 4 different kinds of services. The first one is a really rare service, which is being used by maybe a limited set of users and with like lesser frequency. For example, some fixed function you have been doing, maybe checking some calculation on very rare units. The second one is you have a 3-layer of service chain where you have, for example, you have a 3-tier web application, or maybe, for example, for telco, you can imagine a virtualized enterprise firewall where you have multiple stages, and if you take the whole pipeline inside a software, you would divide it into, for example, the first stage is classification, and then you do metering and some routing, and all sort of packet processing going between those core and core communication. In that we have seen two modes depending on the platform resources available. You can suffice all those 3 services on a single platform, or you might have to go and take a penalty and go to another platform to do the later stages of that service to be done. And the last service model is where you have really a bulky big service and you have lots and lots of people using that. For example, kind of image recognition algorithm running inside that service, and you are giving it to all the IoT devices. Where you have so many inbound traffic, and you have to do a lot many load balancing efforts here. But if you closely look at this, when it comes to a platform point of view, ultimately all the services running in the core in different kind of forms like process, or maybe containers, or pod in terms of Kubernetes, or maybe VMs. But ultimately it boils down to a CPU core, and that's why we have a shared resource and we see a contention effect there. And as far as the latency is concerned, if you go deeper down in the service layer, the service has to travel till the end of the service chain and get back. So we have seen a huge penalty using a Linux TCP/IP stack, for example, for networking, and that's why we have an optimized API for packet access. But as you can see, after all this,
what is the actual problem you see in Linux TCP/IP stack?
So it's been using interrupt modes for basic devices. I mean, it would work for 1 gig device, but if you go to 10 gig device, 40 gig device, and if you want to keep up with the rates of the requirement of data, it wouldn't match up. So that's one of the key problems we have. The second one is it's being exposed to the user level application through a socket, and they have queuing and they have the whole algorithm built up on top of it. So we have seen multiple of bottlenecks there. We kind of took it out over the last 5 years, and that's what we have adopted, at least for comms and telco service provider who needs direct access to the NIC. And in some cases they are okay to use, and some use cases.
You're raising with DPDK?
Yeah. So that's what I'm.
Another housekeeping. Can you repeat the question because we're recording?
Oh, sorry. So the question was what was wrong with the Linux TCP/IP stack, and we have seen maybe more issues with the TCP/IP stack, and that's why we kind of bypass the Linux kernel, take the PCI device inside user space. We have our optimized packet processing libraries, and we have been using huge pages. We have an optimized memory management APIs. So with all that collective knowledge, we have been getting really good line rate and bandwidth utilization on the next front.
So there's one fundamental piece with you process a packet in Linux. It's basically it locks you through a long way of the. So you receive a packet. It does what we call escape of allocation. It uses creates a buffer. It says, okay, is there somebody else that needs this packet? Through that entire process, it applies locks to do that sort of thing for folks that do packet processing. You're probably well familiar with, from memory allocation to make it into the NetIF structure. If you then create a structure, if you then create a socket, there might be a user space handle, right? So there's enormous amounts of latency through that stack, but there's a good reason for that. They want compatibility. Everybody needs to be able to create a socket, grab a packet, do something with it, stuff it back into the Linux stack, and then go into the next service, and then do it again. And that's a really, really lengthy process. That doesn't work very well if you're a communication service provider, because you want low latency, you want to be able, again, back to the premise of the statement. The premise of this talk is, we want to virtualize communication devices. These things are designed for peak performance. If you buy a router, and you want it to do 40 gig line rate, well, it has to do 40 gig line rate, not 20 gig because you have Linux limitations. No, you can't have that. So that's the reason why we build DPDK and all these sorts of hooks along with it. But inherent limitations with Linux is typically memory allocation. That's along with all the other stuff that the Russian just mentioned, but it really comes down to the memory allocator. Oh, there was a question there, I'm sorry.
Yeah, I mean, so you mentioned about in this service chain, service X being slightly light service, and then you go deeper on that. What was your basis of that thing? What do you say that?
So that actually depends on the. Sorry, the question is how do you decide how many levels of service you want to go in, and how many stages you want in your app. For example, if you are designing your app in a microservice kind of environment. Actually, it depends on the programming model and the architecture you have for your application and the scalability. So, for example, not all the service stages will be that lengthy. In some cases, couple of service stages will be like really fast enough and smaller to compensate like 100 or 200 users, whereas the middle big logic block will be processing a lot, and you would need a more to sustain, right? So it's up to the application developer and architect to do it. But this is kind of a generic kind of scenarios we have seen so far, and that's why we have kind of put more focus on it here and put slider here. So
I've read some service training IETF draft. They also talk about taking the service up till at the CP level. Do you talk about that, or?
So the question is, there was some discussion around IETF drafts about taking service chaining and VCP level, right?
Yeah.
So I'm not really sure about. We haven't done any kind of discussion around that.
No, I wouldn't know.
Or maybe I would say there is no standard service framework. So we have all these low-level platform APIs, and then suddenly people came in and take those APIs and making their apps and just hooking into the orchestration. So I think there is a gap in between there where we need a highly scalable standard application and kind of standard APIs for developers to develop on it. So that's where I have, I guess, Google guys will come in and say a few words about their experience with the Google Cloud Platform with gRPC and what they could achieve there, and maybe some good things we can borrow from there and kind of integrate with DPDK and some other platform features. And let's see if we can get best from both worlds.
So you said that you will bypass Linux stack, right? So what about IP, the fragment reassembly and stuff like that? How does that get handled in bypass?
Can you repeat the question?
Yeah, so the question is, if you bypass the kernel and take the whole NIC inside user space, how do you take care of the IP fragmentation and the SRM stuff?
Phenomenal question. You do it yourself. So we have applications that do it in DPDK. There are sample applications that do fragmentation, and there are actually companies that some of you might be here in the room that make a business out of that, right? So they come in and say, hey, this is a great framework. I'm going to go and provide fragmentation support for DPDK.
Think about each one of them, like box them, and then put a star saying there's one CPU core, like all of them is supposed to run within one core?
No, not necessarily, but you can make it. If you want to share the CPU, if you're not able to get the full out of that CPU, if you have still free cycles, you can do it. But this is kind of generic, not specific to DPDK, because DPDK is a completely different programming model. You have whole mode drivers and you have set of optimized.
So for example, the number 2, you have one service 1, 2, 3. All three of them can be on the same core or 3 different cores.
3 different cores, yeah.
But why that was significantly mentioned in particular?
Just to keep in mind that it's like everywhere. They have been using in container, in normal processes as threads, or maybe it's in VMs where you can't directly pin vCPU to PCPU in most cases, and depending on hypervisor actually. So it's been deployed everywhere in different scenarios. So
Nothing similar.
no, not.
We like to consume cores.
That's terrible.
So do you guys have a performance number between your home mode and your interrupt DPDK, and what's the trade-off?
Let's go. Let's move on.
So you mean DPDK core mode and DPDK interrupt mode, or you?
Yes.
Next
Okay.
slide.
Yeah. Maybe. So yeah, this is
skip one forward and then come back.
okay.
A couple forward.
Oh man.
There we go. It's not that bad.
So this is Intel DPDK running L2 forward, L3 forward application processing packet at those levels and the user space. And on the left side we have Linux process. And I believe it's not dispatching it to user space. It's still in kernel and forwarding back. But it still has to enter the whole stack.
No. This is in user space. So we use the UIO framework to get the user space, right? So and it's about 28x performance. And we sustain that. So when you go to new architectures, even though Linux catches up a little bit, we typically do.
So this is
considerably
the
better.
poll mode, right?
This is in poll mode. So that's
what
the.
about the interrupt with the DPDK?
So there are two things.
Actually, yes, we do have numbers. So when you turn on interrupts back on, you incur. It's funny because we just did all this research. You context switch, depending on whether you're in a power state or not in a power state. Let's assume you're not in a power state. When you context switch and you're already in the kernel, right, and you receive an interrupt, and then you hand off to user space. That takes you about 4 microseconds. So you need to buffer 4 microseconds worth of packets. We could keep up with that at 10 gigabits per second. So there was no performance degradation at L3 with 10 gigabits per second. No doubt there are corner cases when you have a lot of interrupts occur. You're probably going to lose some packets. When you go to 40 gig, the situation looks a little bit different. And there are losses, but they're not as big as you think.
So do you have to pin your interrupt to?
We would pin.
Oh,
Yeah, so we have people we call EPOL. And then we are working on some technology way in the future that circumvents all this, but I can't disclose it. Yeah. So how many flows was this? Do you remember? This would be about 1 million flows. So it's not a benchmark completely designed.
Half a million to make it.
This is not a benchmark to complete. This is a benchmark to make DPDK look good. Don't get me wrong. Let's be honest here. There's no doubt about that. As soon as you start doing bigger flow tables, because we're not missing the last level cache, right? So we have big LLC, and as long as we can turn around the packet in the LLC, you're good to go. But as soon as you start incurring misses, it doesn't. This will come down. But so will that.
If you have a lot of VMs on a single box, and each of them doing
No. You hold on. That's where you need more cores, but you also need RDT, right? So we built some functionality that allows you to partition off the LLC so you can do this one. So we get it. We're trying to think this through, and we're trying to do the right thing from an architecture perspective, and we believe that partitioning shared resources is the right thing to do to continue to scale up.
So with the RDT, since you mentioned RDT, so do you get to say L3 cache application name gets 20%?
Yeah, you do. So it's really cool, but I don't want to steal Priya's thunder, you see?
So yeah, and one more point to make is, I guess up to certain bytes, DPDK makes sense for you because it's a very smaller frames, and the interrupts coming in wouldn't be really easy for Linux stack to compensate for that. So I guess for smaller frames, the DPDK would drop, but at higher frame sizes, even Linux TCP IP stack would reach up to 10 gig.
Well, there's no secret if you have big packets, amortize the latency, right, over your locks, right? When you create a lock and you have a much bigger frame buffer, you get more time to process that. By the time you get to process that, the lock is released and you're good to go. So it kind of makes sense. But if you're designing a router, if you're designing some wireless access device, you want that performance at 64 bytes to 128, 256, and only then you start kind of rolling off into that amortization factor when Linux start making sense again.
So is this chart for 64 bytes? Because no
This
one
is
uses
64 bytes.
64 bytes is almost unseen in the application on the router world, right? I mean, unless you are really running a control plane protocol. 64 byte Ethernet packet size.
Yeah, it's not what we're being told, right? If you look at
Voice. Looking at VoIP.
if you look at voice, right?
China.
Small request or even web services, right? Small request bulk response. You know, I buy 64 bytes, but 128 bytes. No, I think that's a pretty common size. 256 bytes, very common, right? And it's that sweet spot we're looking at here. At least that's what we're being told. So.
How many TCP connections are we talking about? How many connections are you talking about?
Millions. This was a million.
So if that's the case, even with Linux stack, it will not probably, I don't know, the collision.
It will not scale. It will not scale. You're correct. Sorry, there was another question.
Which architecture was this run on? It says Intel architecture.
It's Xeon V2, so past 2 generations back. When we take this forward, this, like I said earlier on, this continues to scale.
Can only get better.
So you mentioned this was running in user space. So the processor was intercepting the network with packets. Was that a custom benchmark, or was that for data that's something like OPS?
No, it's pretty custom. It's latency forwarding. So we compare, we look at what Linux does. It looks at the packet header, right? Rewrite does a 5-tuple, then rewrites the packet header, sends it back out. We do exactly the same in our application. So it's equivalent to Linux. That's what
I think we should move on.
Yeah, we need to look because we need to come to the Google.
Do you want to go back or?
No, let's move forward.
So, okay, this was just a view from a very low level 100 feet. So I was just talking about virtualized enterprise firewall stages and how all those different stages may run on different ports, and they have software queues between them to exchange packets. So the key point I wanted to highlight was the shared resource here, where you don't really know and control which core uses how many cache lines and DRAMs from your socket. So and then once we take the whole network function inside virtual space and running DPDK there, everything is now an equation of cycles on our code. So the cycles you spend here missing L2 or L3, it'll be directly proportional to the performance you get in the pipeline. So that was the key point there.
Question, sorry. So, sorry.
No problem.
What do you use to implement your software queue on your last slide?
So the lockless queue, we have a lockless queue implementation in DPDK. It's RT ring. So it's using atomic operations.
This is the cool thing, right? We like these lockless queues because they give you performance, but at the same time, you need to port your application to these queues. It can be painful. This is where the Google guys come in, right? So this is where you want to abstract that and be able to use like an RPC to communicate between these individual, compute elements. And that's kind of the connection we're trying to make, right? Trying to say, hey, it's great to code to all these APIs, but it's all about scalability as well. So if you define these interfaces nicely, you can scale out your load balancer, which is something Jayant will talk about.
Sorry, I mean, even in case of millions of connections, you still need to, for example, user level TCP, you still need to log the TCP.
Sure.
For that particular thing. That will incur a lock. It depends on which bucket you are following.
Yep.
And if there are multiple connections, you're going to hold that entire bucket. So all the problems will be there with locking. Unless you redesign that as well as lockless.
Correct. It is, so the question really is, okay, if you want to scale performance, you need to get rid of locks. And the answer to that is yes. That's why we built these APIs to do, lockless queuing. This is also the reason why we want to extend these lockless APIs to work with layer 7 services that allow you to then scale out your application without you needing to know about these locks. Okay?
Just move, so for all those latency sensitive requirements and high throughput scenarios, what do you need actually from the platform? So some of the key platform features I have highlighted here, that we have virtualization technology, RDT, memory controllers, NICs and crypto and hyper-threading. We can control all of this somehow, but the real programmable control is only available in the RDT through the APIs we have been building. And then in the software layer, you can have multiple libraries optimized for those devices, where the DPDK would fall, by Hyperscan, it's in DPI if we have on IA, which is optimized really for IAB code. And then we have QAD API, which uses our crypto devices and offload your crypto workload on the engines we have in the PCI device. And then some of the OS kernel optimizations as well, which we need to glue all these things together. But you know what? In most of our industry interaction with the folks doing public and private cloud deployment, I have been missing a standard service semantics which glue all these APIs together and show a nice and standard API sets to the developers, where developer can give some hints about their services going to use on that platform, and then it can be orchestrated on the choice of orchestration software you have. So throughout that whole journey, I don't think I can cover it up, or maybe we can cover it up. So we'll be focusing on three aspects. One is optimize IO access. So I guess we talked about DPDK a lot, and then when it comes to shared resources, we need to protect those shared resources and avoid the contention. So that's why quality of service comes in. And at last, how do you expose those cool hardware features to developers so that they can develop an kind of service or a specific tangible thing, and that can be orchestrated easily and can be handled in the hardware. So I guess I'll jump. So this is all performance stuff. So I hope you guys are aware of.
Basic question here, just pausing you. So you said that bypassing the Linux stack by using the DPDK in the user space, right? And that makes the Intel architecture usage much better for the networking. Why not make it part of the Linux distribution if it is such a stable and open way of doing it? Everybody needs to, according to what it looks like, everybody needs to develop applications or use the stack in the user space. So why keep that limitation for the poor layman to figure it out? And every company, every engineer needs to figure it out, how does DPDK work and make their application work.
I guess, I mean, those kind of experiments.
Can you repeat that question?
So the question is, why do you do it in user space with DPDK? Why don't you put DPDK in Linux kernel itself, and why don't you get an optimized driver in DPDK in the Linux kernel?
No. I say expose the DPDK in the user space and let Linux also work in the user space, all those applications. Make this part of the user space within the Linux system. We've tried. That's right. Yes, the question is why does the Linux community not program to this interface? And actually the answer is right? So as part of Red Hat Linux, right? MJ?
Yeah, I think it's in
RH, right?
Red Hat Linux. They have those.
I don't know which version, but it is there. But let's qualify what you say a little bit, right? Because what you're requiring is all the legacy that exists in the kernel needs to now ported forward to DPDK. That's a lot of work, right? So let's qualify that a bit, like Nginx, right? Or So
well, and you've got other vendors,
of course,
microprocessor vendors who may not support this.
Well, then, hold on. We'll get to that in a minute. No, this is you look forward in the deck. We actually did build an ARM port. It is actually available. It is truly an open source program. But just to force everybody to start using DPDK, that is a tall order, right? We can't. That's not the objective. The objective is to build communications appliances with this architecture. Right? If there are other solutions that might benefit, maybe there is a port in Nginx that might help, that might benefit by this. But we're not trying to force that. Right? There's plenty of other applications that you might not want to port for. Sorry.
Yeah, so I think questions now, we have to move on.
One
hold the question.
So
exposure of EMD to upper layer, since we've been talking about scheduling frameworks, Kubernetes and such. I mean, from single compute node, it's kind of obvious what you could do. Now you're talking about exposure to a pod where you potentially might be covering many different compute nodes. So last time I looked, it was quite abstracted and very difficult to use. Are you doing anything?
Yeah, I think so. So things like we're making an IP stack, right? So which make it, you can just get a DPDK based socket, right? So those are the kind of things we're building. I'm not sure if they're mainstreamed yet. We have some. We're trying to port things like lightweight IP stack to DPDK, so people can take advantage of it. We're supporting a multitude of architectures, so we're not only limited to Intel architecture anymore. So it is a truly.
It wasn't my question. When you have more than one CPU, physical CPU, how do you represent it?
Gotcha. Sorry. We have lightweight threads, so we're trying to adhere to a new mechanism by you create a thread, and it doesn't really matter where the thread is going to run. So you can create a new style thread that the operating system will take, and it will run it wherever you want to. So you don't have to tie it to a particular core anymore. So those are some of the things we're doing to try and ease that physical requirement to pin a thread to a core.
Even if the core is on another physical machine?
No, not yet. That element is not yet. Okay. That would be like migration, but let's take that offline. Okay, let's move on.
You mentioned Kubernetes, so
yeah,
you should.
So it's in planning.
Or at least in concept, what we thought. So it's been assumed that it's just an Intel architecture and Intel next supported in the DPDK API, but lately it's been an really open source community, and we have some key industry players who have been contributing their core driver codes for their NICs, and we have multiple architectures supported like Power 8 and ARM as well. So it's like completely open community, and anyone can go and submit patches if they want, and if they think that can be really useful for the next generation of networking.
So in the interest of time, sorry to interrupt. In the interest of time, so you'll have these slides available. The rest is kind of about code samples and some of the APIs that we have available. Look at them at your leisure. Our contact details in here. I'd like to switch to RDT, and then we'll do that. It takes about 20 minutes maybe, and then we'll switch to the Google team. I really want to give you, sufficient time to get through your slides.
So just one point to make here. So all this DPDK APIs, so DPDK APIs is the raw packet IO access API. It's not doing any beyond layer 3. It's just accessing frames from the NIC very efficiently, and turns around in the budget cycles it has on the code, and it tries to reach the 10 gig line rate or 40 gig line rate. So all of these applications must be ending up around layer 2, layer 3, and it will be forwarding packet back out. It's not an endpoint, so it's not going to process up through the stack and going to the presentation layer. I mean, if you're trying to put a browser on top of that. It can be an option, but not all. And some of the virtualization support we have in DPDK, and different virtual devices are supported. So maybe you can look at it a later time. Okay. Now about shared resource content.
Okay. So thanks Rashmin and Edwin. Both of you helped us to understand SDN, NFP environment, and how things move there. So we have base set up here, and we understood from all of this that when we have software-defined infrastructure, there is a consolidation of various workloads, and they run in parallel. And these workloads will be, cloud service providers, will be communication service providers, or enterprise. So given all this understanding, we realize that all these workloads will run in parallel on AI processors. So when these workloads run in parallel, we have seen that there is a shared level resource contention which could lead to performance degradation. So what are these shared level resources in I/O? So it's a large level cache, memory, and I/O. So with our study, we have found out that when you have streaming nature application, which could pollute your cache and become a noise to application of your interest. Also, I'm going to follow up with this study further, but we have seen that there could be 51% of throughput degradation when different network functions deployed on I processors. And I'll talk about it in upcoming slides. So in order to, just to get rid of all this shared level resource contention, Intel has come up with this technology called Intel's Resource Director technology, which consists of these three features. So I'll call them out as cache monitoring technology, memory bandwidth monitoring, and cache allocation technology. And cache allocation technology also consists of code and data prioritization. So why these technologies are there? So first two technologies, CMP and MDM, will help us to profile our applications. They will let us know that how it is performing on shared level resource contention point of view. So once you understand all these statistics from CMP and MDM, you can take that knowledge and use cache allocation technology to enforce and use partitioning on these shared level resources and achieve 50 attributes. Someone just spoke about it, like lower latencies, higher throughput, and compute power. And you might have one question like, okay, how does it really differentiate between existing telemetries you already have, like perfmon or node manager? So one thing we have to remember that all these three technologies, rather four, they actually help you to take hardware, advanced telemetry into your scheduler or in your application. So you can do a feedback loop in order to get higher performance and prioritize your applications.
So does it need a change in the app layer?
Sorry?
To leverage these three properties, does it need a change at the application layer?
Yes, so the question was, do we need an application layer change in order to adopt these technologies? And answer is yes, and I will cover that aspect and how we are enabling that for the community. So this is in-depth view of how these technologies really look from I point of view. We have DRAM, we have last level cache, and applications running on these individual ports, which are increasing nowadays with humongous number. So you can see that with CMT and MDM, we can find misbehaving applications. Once you find such misbehaving application, you can use cache allocation technology to partition such application based on your requirements. There could be higher, like gold, bronze, and silver services, which you want to prioritize onto your platform. And one thing can be also done is code and data prioritization, where you can provide code and data masks onto your last level cache shared level resource. So I think we know enough about this technology. So next question is, what we have done by taking this technology, and what is the applicability of this technology into industry? So we have been doing research with UC Berkeley to find out how it really fits into how actually RDT can help into edge devices. And so motivation behind this study was to simultaneously run multiple network functions. As you can see, like we are running SNOD, MASNet, IPsec, and you name it onto IA platform, and while consolidating such workload, achieving quality of service. So, this diagram just shows what was the setup like and what was our motivation behind this study using RDT. So, okay, here you go. So when we have deployed such network functions on I, we have shared level resources, as you can see, and the one which I'm talking here is last level cache. So when these network functions running simultaneously on this platform, given individual cores, 64 bytes packet size, and 100K floats on each of these network functions, you can see the throughput degradation is up to 51%, which is quite a large amount when you think of deploying and consolidating huge number of workloads onto IA platforms. So what we wanted to do here, use RDT as feature to reduce this noise and get our performance back to original. So we use CMT. Oh, sorry. Okay, I think I'm loud enough.
No, it's not.
Oh, okay, good. Okay, so we use cache monitoring technology and cache allocation technology hand in hand to see how our applications are doing on this platform, finding out exact cache ways in the sense cache partition or cache size it needs to perform up to the mark. And now you can see that we just have 2% variation here to achieve to the to the ideal goal where we have the SDI and NFV characteristic where we want higher throughputs. So okay, we were happy with these results. So second question I heard was latency. Okay, go ahead. Sorry, I missed the question.
Is there a performance impact by using CMT?
No, not really.
So it's passive.
Yes, so we use a very slick infrastructure called RMID, which is architectural. You can take those hardware hooks which are smart enough to find out what's going on to your core, and it doesn't have any performance impact for these monitoring features. So okay, so someone was asking about latencies, and
Priya, can you move the mic closer to you?
Can you guys hear me? Okay. So we moved on to latencies and find out, how latencies would behave when we have noisy neighbors. I thought that.
I think
No?
it's not catching your voice.
Can I get?
It's working.
Okay, it's working now.
Oh, just put it right.
Swallow, plug it in.
Okay.
Swallow.
Sorry for that. So I'll get back to latencies. So when we ran, again, all these network functions which were creating noise for each other, and we see that our latencies were quite huge. The moment we used again CMT and CAD together,